So, welcome everybody. This is a talk I'm giving for the second time, so hopefully it'll be better than the first time. We're going to talk about lambdas. We're going to talk about C++11 lambdas and C++14 generic lambdas. And we're also going to talk about a couple other functiony sort of things that you may confuse with lambdas. Show of hands, first of all, how many people think they know lambdas? Right, this is way more hands than the San Francisco meetup. All right. And the name of this talk is Lambdas from First Principles, or from scratch, depending on who's telling you. So we're going to start at the very beginning. We're going to start with just regular old functions. These are regular functions like you would have in C, right? The most basic thing possible. Let's make a function. Let's call it +1. What it does is it adds 1 to its argument. And this is what it looks like. You got some C++ code, which also happens to be C code. And on the right-hand side, we've got the assembly that this generates. This should all be very straightforward. If you haven't seen assembly before, note that what we've got here is a unique name for the function. Happens to begin with a bunch of underscores and end with an I because this is C++. And we mangle all our names for reasons that we'll see in a moment.
Sorry.
I got an echo. And the code below it is the code for adding 1 to a thing. Okay, let's move on to something more interesting. What can we do in C++ that we can't do in C? We can do function overloading, for example. This is where we have the same name in C++ for two different things, two different functions, say one that takes an int, one that takes a double. We can dispatch on the argument type. How does this look in assembly code? We have two functions, and you'll notice that one of them has an I. One of them has an I and one has a D. The one indicating int and the other indicating double. And the code inside these functions looks very different, even though the code in C++ looks the same. Right? They both say return x plus 1, but of course, when x is a double, that's different code from when x is an int. Okay, that's very straightforward. But this is a little redundant, right? We don't actually want to write code like this all the time, where we're stamping out multiple copies of this for every type that we have, where all we're doing is returning x plus 1. What we really want is some sort of function template that we can stamp out copies of this for any type at all. So we have that, function templates. Here we have a function template +1, and we can call it with an int, we can call it with a double. Or I say we can call it, but what I really mean is every time in our source code it looks like we're calling the thing called +1, what we're actually doing is stamping out a new instantiation of that template. And so our assembly code looks like what we have on the right, which looks exactly the same as on the previous slide. It's just that the names are mangled a little bit differently because they're instantiations of a template instead of overloaded functions. And let's see, is there anything else to say about this slide? No. Let's keep going. Get the good stuff. Okay, yeah, there's actually a bunch more stuff to say about it, isn't there? Right, so on the argument type, you can actually, compiler will actually deduce from the argument type what the template type parameter t is supposed to be. So we call it with a double, it instantiates with t being double. We call it with int, it instantiates t being int. It will also deduce in a couple other places, which is actually kind of interesting, a little bit of trivia. For example, if I use +1 in a context that requires a very specific function pointer type, for example, I can take +1 and assign it to z, which is a pointer to a function taking int and returning int. The compiler is smart enough to know that in that case, t must be int. That's kind of cool. Moving on. Right. Using the name +1 in other contexts where we can't deduce what exactly you mean by +1, is an error, and the compiler will diagnose your error. All right, enough about function templates. That all makes sense? I said whirlwind tour. Class member functions. This is something else we can do in C++ we can't do in C. We can have a class. We can name it plus. You can have a function inside that class called +me. which takes the implicit this pointer, and you know how member functions work. And in assembly code, they look pretty standard. We've got a constructor there at the top, which is mangled with a C1, C for constructor. And we've got the plus me function, which is mangled with it, the name of the class plus, and the name plus me, which is the name of the method. And you'll notice that it also ends with an I, being that it takes an int. Okay. Right, now you might ask, this is how you would use the code, right? You'd say, I'm going to make an instance of plus, I'm going to construct it with the value 1, and then I'm going to call plus me on some other value. And of course, we want the answer to be 43 if we're adding 1 to 42. So how do we know that when we run this code, we want to call this particular version of plus me and not some other? How do we get from the call site to the actual callee? The answer is very different in C++ than it is in Java, right? In Java, it looks like this, right? You've got your plus variable that lives on the stack. Then you instantiate a plus object of class type that lives somewhere off on the heap. That class knows everything about its behavior. It knows that when you call plus on it, it needs to go to its plus method. And it does this via virtual dispatch. It has a vtable somewhere. Lots of pointers. Pointers all over the place, memory management, all sorts of stuff that we don't want. C++ lets you do this, virtual methods, but it's not the default. Default is plus is, in fact, a plus object itself, not a pointer to 1. It has the value member inside it. And there's no pointers involved here. It's just when we do the call, it's a call to the member function plus me. That's just sort of magically linked through the magic of static typing. Objects of type plus are just magically linked up with the code that implements the behaviors of type plus, and nothing represents that at runtime. All right, C++ is not Java, right? Class member functions. Okay, so what else can we do in C++ that we can't do in C? We've covered overloading and templates and member functions. Operator overloading. C++ lets us overload the basic operators in various ways. For example, instead of calling this thing plus me, we could just call it operator paren. We could call it the call operator. And you'll notice the difference here is that rather than calling plus me, we can just say parentheses, and that knows that it's going to call operator paren, again, through the magic of static typing. And you'll notice the mangling is a little bit different and so on. But again, we all know this. We can overload operators. But knowing all of this, we can actually make something kind of nifty. We can take this code that we just wrote for class plus that captures this value and adds it to its argument. And we can take all of that boilerplate that I've written in green. That's all reducible complexity. There's certain amounts of irreducible complexity here, such as the fact that we capture value and that we take an int argument name that we're going to call x because we need to use it to say return x plus value. And all the stuff in red is stuff that we really can't get rid of. It's irreducible. But all the stuff in green is just boilerplate, and we'd like to get rid of it if we can. Well, in C++ 11, although I'm mostly going to be talking about 14 here, so let's pretend that 11 doesn't exist. Let's just talk about 14. In C++ 14, there's a syntax for this. We can take all that green stuff, boil it down to this green stuff, which is much simpler. You just have a whole bunch of brackets. One of each, actually. So you just say we're going to capture a thing called value. We have an argument x. We return x plus value. Value's initial value in this case is 1. So we've taken all of this red stuff and kind of rearranged it. We get that. And it does exactly the same thing. Yes.
Sorry for that. I just not recording the content. Sorry for that.
Oh.
I selected a wrong window to this record.
I go full screen, it will still work. Oh, nope. Just
Yeah.
drag that over there.
The one question.
Yes. Question.
So with this, the assembler code is same from the previous class-based class.
Yes, these two are, for all intents and purposes, identical.
Really?
Yes. The fact that in this one we have our boilerplate here that has to have a couple of names at, right? The capital P plus there is a name that we have gotten rid of. It's replaced, the compiler replaces it with a made-up name that we don't have access to, which we're going to see in a moment. But basically, yeah, this creates an instance of an object of a class whose name we don't have access to. It has a member effectively named value. I mean, in the compiled code, the member names don't matter anyway. But yeah, it's got an operator paren that is even const. Does exactly that in the back. Yes, the name Lambda comes from Lambda calculus and is. We're not going to talk too much about Lambda calculus or Turing machines, but the name Lambda basically just comes from the fact that they're called lambdas in, I guess, Lisp and other languages like that. It's an idea that we're taking code and data and bundling them together into these things that behave sort of like functions that have captured parts of their environment, right? Like in this example, we're capturing one from our environment and then using it with some code. And hopefully coming from this direction, it should be reasonably obvious why you would want to do this in a real program. It's less obvious, like, what are the mathematical ramifications of this? But we're going to see a real-world example probably on the next slide. Yeah, I know that if you look up Sumant Tambe's presentation called Fun with Lambdas, he comes at this from the opposite direction, starting with, here are generic lambdas, they do something magic, don't worry about how it works. Let me show you how you can build the identity function and the function that returns a function and things like that. So if you want the lambda calculus side of things, I guess I would recommend Fun with Lambdas. He's got it somewhere. Yeah, Google that. All right, I'm gonna say yes. Very next slide has both this made-up name and actually that's all it has, made-up name. But we're getting there. All right. This is the exact same implementation. This is the exact same diagram as there was on the previous slide with plus and plus me. All I've done is change some of the names around. Plus is now no longer a plus capital P plus object. It's now I'm going to call it $_0 object. This is a name that we don't have access to in our source code, but this is Clang's mangling scheme. So if you use the Clang compiler, you will see the assembly code up here on the top right, where again we've got a call to a constructor. Whose constructor? $0's constructor. And we've got a call to a call operator, a function call operator, which is $0's function call operator. And again, no pointers or any sort of dynamic memory management or anything going on in the code. They are linked through the magic of static typing. Add an inline to that somehow.
I mean, it's such an obvious thing to say x plus value or values determine the compile time and have the efficiency of inline.
Yes. In fact, I had to do some terrible things to the compiler to get it to not inline this code. Yes, if you're using Clang, you will not actually see the code on the upper right unless you turn off inlining, and like you have to do a lot of stuff to get to persuade it that really you want it to generate call operations, because normally, yes, I mean, the compiler with a Lambda, because of sort of a quirk of the syntax, in order to use a Lambda, because you can't name its type, it has to basically be right there in the source code at somewhere in the translation unit that the compiler is looking at. And so the compiler definitely knows the code. And so when you call it, you're calling the function call operator. The compiler definitely knows what that function call operator does, and therefore it is almost certainly going to inline it, which means Lambdas actually get you very nice performance. And yes, I had to turn off those optimizations in order to get this code to look like this. So what have we got here? So we've got basically Lisp-style closures. They can capture data from their environment, and then they have behavior that goes along with that. But we don't have any of that horrible Lispy stuff that we were afraid we were going to get, such as dynamic memory management, garbage collection. We get to keep our static typing. We don't have to go into some sort of dynamically typed realm. We have all these nice properties of C++. We get to keep them. So here's an example. I'm calling this sort by property. And what this does is it's going to take a vector of what you can think of as like JSON blobs, except that I'm simplifying them and saying that they have string keys, and then they just have ints on the right hand side. So an object is a map from string to int, and I've got a whole array of these objects that I want to sort by one of these keys, sort by the value associated with one of these keys. So I'm going to pass in the property's name, or I guess the key's name would be another way to put it, as a std string. And then I'm going to call std sort on the vector. And for the comparator that I pass in to say, here is how you actually compare two items and say whether one is less than the other, I'm actually going to compare the value associated with the key prop. Oh, can you actually tell that there's a difference in color between those two? It's very subtle. It's clearer on the screen. But yeah, the P here is a slightly lighter purple than the word prop. And what this is indicating is that P is the name that we're using inside the Lambda, sort of the name of the member variable of the Lambda class, and prop is the name outside. And what this is actually doing is, okay, we have our std string prop, and so we have prop is on the stack, but of course, being a std string, it dynamically manages some memory out on the heap with the word hello in it, right? And assuming that we don't have small string optimization or anything else, we're going to simplify, we're going to say it's on the heap. So what does it mean when we copy a std string? It means we actually make a copy of it. So P is a copy of prop, and it has its own hello. And P-less, our Lambda, holds that copy. So that means that we can then get rid of the original one, perhaps. Oh, I'm sorry, we're not there yet. But yeah, we could get rid of the original prop and still have the copy. Okay, so this, by the way, is C++ 14 syntax, where we get to explicitly say, here's the name I'm using inside the Lambda, and here's what it was outside. Here's the thing I'm capturing. Here's how I initialize it. There are some simpler syntaxes for this. We can omit the equals sign entirely and just say its name both inside and outside is prop. That's like prop equals prop. Same deal. We can even drop the name altogether and just say, you know what, any name I use inside, just assume that it's initialized by copy from outside. And we do that by just saying a sign. These latter two syntaxes have already existed since 2011. The very first one I showed and the one that I like the most is 14. Okay, right. And then here we finally get to the semantics of it. We can get rid of the original prop at any point, and our lambda still has its copy, which means we can pass this lambda around, we can pass it out of the current function, and it gets to really capture data with no garbage collection involved, right? Because it made a copy. That's great, but of course copying is slow. You don't always want to make a copy. Right? Sometimes what we want to do is sort of capture a reference, and we want something that looks like this, right? Where instead of having this big, expensive prop, we want to have a very small prop pointing to the other one. So how do we do this? How do we capture a reference in our lambda? Well, there are a couple ways we can do it. Possibly the easiest one is say, okay, we want a reference, make a reference. Std ref of prop is going to be a std reference wrapper, which behaves in pretty much all cases, not all, but pretty much all, as if it were a reference. And then we can just write this code and it just works. But capturing by reference is such a common use case that there is a syntax for it. If we just stick an ampersand on the front of our P, then it becomes a reference. If you write P equals ampersand prop, you're capturing the value of ampersand prop by copy, the ampersand prop being a pointer to. But then you would have to use star P in your lambda. So that would work just as well, except you would have more stars. We don't like writing stars in our code, right? No raw pointers. Of course, here we have raw references, which is not really so much better. But so you can do it like this, or in C++11, you can capture it as long as it has the same name inside and out, or you can just capture everything entirely. Yes. Yes, this still works in 14. It's just that, it's probably reasonable to use this in 14 too. It's just for pedagogical reasons. You know, I really like the ability to specify, here's an expression that is used to initialize this thing that I'm going to have as a member inside my lambda, right? It makes it very obvious what's going on, which is, of course, the whole point of the talk. So, but just for confusion's sake, we'll add that you can do this, or you can even do that. And that just means capture everything in the current scope by reference. Now, you might ask at this point, wait a minute, capture everything. And earlier you showed how to capture everything by copy. Isn't that ridiculously expensive? You're copying everything? No, the compiler knows, and in fact the standard forces it to copy and capture only the things that you actually use. You don't have to worry that putting that little equal sign in the brackets is going to cause all of your copy constructors to get called. It's only going to copy construct the things it needs to. Ampersand is not a copy, so there it's capturing by reference. But you would still imagine that the size of your lambda would get very big as it puts all these pointers in there. And the answer is still no, it only puts the pointers that it actually needs.
Do you have any default capture type? You don't have anything in there.
Ah, yes. How do we figure out what type of thing is being captured? Like, we go all the way back to the very beginning here. Like, how do we know what type P is in this example, right? We never said what type P was. And the answer is auto. So in this case, because the right-hand side of the equal sign is a std string, and it works just like it would work if you said auto P equals prop. So P becomes a std string. So in this case where we're capturing by reference, prop is a std string, and so P is a reference to std string, the std string ref.
Let's say if you don't have anything in that, capture.
Like that. Oh, completely empty. Well, in that case, then you're saying I'm not capturing anything. And if you try to use prop inside your lambda, it's going to say you haven't declared that. and you get an error. Yep, P equals did move prop would move the thing. There's no capturing by R value reference. You can't say ampersand ampersand P equals prop. That won't work. I don't know if there's really a good reason for that other than they just thought, well, no one would ever really want to do that, so let's not make a syntax for it. Yeah, if you want to make a copy of something, there's a nice syntax for that. If you want to get a reference to something, there's a nice syntax for that. If you want to make a copy by moving, there is no real nice syntax for that, but you can now do it in C++ 14 with the explicit, P equals std move of P. In C++ 11, there's basically no way to capture by moving, because, yeah, there's probably a way to like sneak into it somehow, but basically no. Well, you don't have the P equals prop syntax.
No, std move prop.
You mean bracket std move prop close bracket?
Yeah.
No, that's not valid syntax.
It's not going to get the value.
That's just as invalid syntax as open bracket 42 close bracket. It doesn't. It's just not allowed by the grammar. Yeah. All right. Right. And in this case, we're capturing by reference. This is great as long as the thing exists. Of course, you have to watch out that once the thing goes away, you have a dangling reference. So watch out for that. Scott Myers has a chapter in his book, Effective Modern C++, on lambdas, and he says, watch out for default capture mode of by reference, because you can end up with dangling references. And also watch out for default capture mode of by copy, because sometimes you copy really expensive things you didn't mean to. Basically, watch out for default capture modes all the time. There's always going to be a problem. But that's the way it is. You get safety and what's foolproofness, right? Just copying everything, but you don't get speed. Or you can get speed, but you don't get foolproofness. Question?
Context of the lambda, we can always convert that to the strong pointer and then see if we still go to the reference.
So smart pointers, shared pointer and weak pointer, you can use those to solve dangling reference problems, but that implies that you're already doing memory management. You're already putting things on the heap. And notice in this example, we don't have anything on the heap, right? We have a std string on the stack and we have a reference to it. And when that goes away, there's nothing we can do.
I was going to add a garbage collector would solve this problem.
But again, we put everything on the heap, right? You can't garbage collect the stack. Yeah. All right. And this is obvious at this point, but just to drive the point home, we have some non-color-coded slides here. We have a good increment by that captures y by value, and a bad increment y that captures y by reference, and the good increment by works and the bad increment by doesn't, because as soon as you return that lambda, you've popped y off the stack and you have a dangling reference. Right. Other features of lambdas, lambda trivia. Yes. Can you capture everything by const reference? Basically, no. I'm not sure that that's useful.
Yeah, I can't really. When you're talking about things that are local to the scope where you're defining the lambda, so. Well, you got. But if you don't make it lifetime extension, it is const reference.
No, well, if you capture it by reference, you can still modify the referenced thing by default. yeah, there's no way to say I want to capture everything by reference, but also please prevent me from modifying the reference things. You'd have to like explicitly make copies of all of these. Yeah. Can you what? Well, you can explicitly capture things by saying like P equals did cref of prop and Q equals did cref of, but if you just want to capture everything that way, there's no syntax for that. Reference to const. I mean, same thing. All right, other features of lambdas, lambda trivia. Lambdas, you might say, well, if I have a lambda that represents some certain behavior, can I convert it to a function pointer when I need to? Because maybe I have something that takes a function pointer. And the answer is actually yes. Yes, you can, as long as it doesn't capture any data, right? Obviously, if it captures data, you can't make a function pointer out of that. But if it has no captures at all, then yes, you can. Let's see. Can you capture things with static lifetime? File, scope, global variables, static variables, things like that. No. The standard committee just sort of decided that that would sort of be wasteful, right? You're saying I want to use these things inside my function, but they're not exactly part of the current environment because they're part of everyone's environment. And so I don't really need to make copies of them inside my Lambda. I can just use the global one. I can see it. It's right there. No, you're just like if I try to use a global variable, in fact, here we go. Here's a puzzle. This will answer your question. The question is, what does this code print? I will take hands. Oh, and you're going to make me figure it out too, right? It's a good question. Yeah, I hear a lot of 2111s, and that is, I believe, yes, that is the correct answer. This is the wacky behavior of global variables in lambdas. That in the kitten case, we're just saying I want to capture everything by value, and then we go and we use G. The compiler looks and says, "Oh, G. Oh, you mean the global G? Okay." And the kitten doesn't capture anything. Whereas the cat very explicitly says, I want a local variable, or I want a member called G, and I want to initialize it to a copy of G. And the compiler looks up that purple G, the darker one, and says, okay, that's 10. Okay, you're going to get a copy of that. And then in main, where we change the global G, the kitten who didn't capture anything does see the change. The cat doesn't care about the global G anymore. It's already made its copy. And you might ask is that there's a middle ground, ocelot. Ocelots are illegal. Can't do this. This is the C++11 syntax where I just name the variable and I don't use the explicit init capture syntax from 14. This is ill-formed. This is a warning in GCC, an error in Clang. Good question. I believe that GCC will capture G and give you a local copy of it, so it'll behave like cat. Almost positive. Yeah, so this is unfortunate. The error here is that we've said, it looks as if we've said, I want to capture G. And the problem is that lambdas don't capture global variables. You can't capture G. This is global, yes. Not inside a function.
Yeah,
I thought, can you go back to the previous?
Well, cat uses the init capture syntax from C++ 14 that says explicitly, I want in my scope to have a variable named g, that's the left-hand g, and I want the initial value of that variable to be this expression, which is g, which is the purple g, this is the right-hand g. G is 10. Okay, so you want a local variable named g with the value 10. Okay, I can do that. Right, what's not allowed is to just say, I want to capture g. Or, well, you sort of know which g, and which g is the global g, and you can't do that. You can't capture a global or a static local or anything like that. But yeah, GCC, if this is why I always compile with all your warnings turned on and your warnings turned up to errors, because in the first time I gave this talk, I did not even realize that this was an error, and someone asked. What's that? No, you cannot capture globals by reference either, again, because the philosophy here is that if your Lambda actually wants to use a global, like everybody by definition knows where the global lives, right? That's the whole point that it's global, right? Anyone anywhere in the program can see it and use it. Yeah, you wouldn't want to capture cout. Yeah. You wouldn't even want to do it by reference. Why would I? Yeah, if I wanted to have a Lambda that did cout, hello world, and then did endl, it's using all of these entities that are global. But do I really want to, in my Lambda, have here's a pointer to where cout is, and here's a pointer to endl, and here's a pointer to printf, and so on? No, I just want to use them. I don't want to capture them.
I'm not sure if this is the same misconception that one of my colleagues had, but if you're thinking of making this polymorphic, that goes into the parameter list, not into the capture block. If you want it to be a polymorphic output stream that you can pass into the Lambda with each use, that's in the regular parentheses, not in the square block. If you wanted to have cout or a file object or whatever on different calls to Ocelot, then you would make that a parameter to the
right.
argument list, not Lambda capture.
Yeah. Or I could make a Lambda that captured a particular stream, that I don't necessarily know up front which O stream I want to capture, and it might turn out to be cout or it might not. But if I'm just making a Lambda whose whole purpose is to print hello world, I don't actually want to load it up with captures. Right.
Why capture it by reference? It's already there. It's a global reference.
Yeah, it's.
Sure, you can.
Yes, you can. That's the whole point.
I mean,
yes, that's the whole point. Yeah. For example, main, for example, when main uses cout, it knows where cout lives. In the same way, the body of the Lambda knows where cout lives. It doesn't need to capture it. Okay. Go back. Lambdas may have local state, but not in the way you think. We're getting to that. In fact, I think that's puzzle number 2. Here's puzzle number 2. Okay, so what we're trying to do here is I'm trying to make I've got this kitten factory named makeKitten, and it's going to return a Lambda. And I want to have some sort of mutable state that this Lambda can use, so that when I call it once, it gives me one answer. I call it again, it gives me a second answer. So how do you do this with normal functions, right? You make static local variables, right? If I have a regular function and it has a static int a equals 0, and I return a++, every time I call that function, I get a new result, right? I get 0, and I get 1, and I get 2. So I want to do the same sort of thing with a Lambda. So I try it the naive way, and I do this, right? Here I've actually got 2 statics. I've got one in the factory function, and then I've got one outside, one further inside. in the lambda itself. And the question is, what does this print? And I don't feel like figuring it out myself, which means you guys probably don't either. But here we go. What we've done is I've made two kittens using my kitten factory. And I call the first kitten twice, and I get 2133. And then I call the second kitten twice, and I get 2638. So the first kitten has interacted with the second kitten, which means they're actually sharing state here. In fact, neither A nor B has been captured. This is what we end up with. That's the same code, just reformatted a little bit to fit on the slide. We have our static A, which belongs to the makeKitten function. And do I have to, oh, wait, a little cursor. Here is this A. We only have one of them because we only have one makeKitten function. The makeKitten function has a static int A, so there's our A. There's only one of it in the static lifetime. And then there's B. There's actually only one B. The B is the static int B that belongs to the lambda that is inside makeKitten. And there's only one of them. So neither of them actually get captured because they're variables with static lifetime. The only thing that does get captured is C, because it's captured by value. And D, of course, is the argument of the function. And so this is what it looks like. We've got K1, which is a kitten, which is captured its C with value 1, and K2 is captured as C with value 2. But they're both sharing A and B. We failed at our goal of giving them each something that they could mutate at will. In other words, this is what we ended up with. We have K1 and K2, they each have their own C, but just making a static int B inside the lambda did not do what we want because you can't capture things with static lifetime. Does that make sense, by the way? Think about that, and think about how that relates to if I have a static inside a member function. Right? This slide. Because remember, this lambda syntax is really just syntactic sugar for making a class with a call operator. And that's a member function. And you put a static inside the member function, there's still only one of it. We didn't magically make multiple statics. So we ended up with this. We have a single static B. K1 and K2 are both using it through the magic of static typing. So we failed for a time being at getting our mutable state into these. So how do we do that? Where do we want B to live? Oh, actually, yeah. Here you see that K1 mutates it, and then K2 can see the update. That's not what we want. What we want somehow is to get our stack to look like this. We want K1 and K2 to each have their own B, so that then when K1 mutates its B, K2 doesn't see the change. But how do we do this? Remove static. No, that would just make it a local variable. It wouldn't keep its value, right? We want to keep its value. So how do we make that happen? No heap. The heap is still empty. We're not going to use dynamic memory management. Yep, we already have the syntax for this. We do the exact same thing we did for C, right? We got C there. Let's get B there as well. So let's capture 0 by copy and call it B. The only wrinkle here is that by default, you can't mutate things that you capture by value. They get captured effectively as if they were const. This is also sort of true of references, except that you can't really have a const reference. All you can have is a reference to something that's const or non-const. And in fact, the reference you capture is a reference to something that is non-const. But things captured by value, the committee decided basically you usually don't want to modify them, so let's not allow you to modify them by default. And the way that we do this is we make the operator paren be a const member function, so it can't modify the members by default. But add the mutable keyword after the argument list there, and that makes all of your members mutable. So now C is mutable and B is mutable. Actually, that's not quite true. They're still just plain old non-const, but now your operator paren is no longer const either, so it's allowed to mutate them.
There's no way to selectively apply mutable to a capture.
There's no way to selectively apply mutable to the capture block. That is correct. Yes, mutable is all or nothing. So in this case, we could accidentally modify C, even though we didn't mean to, if we said C++. But why would we say that? That's ridiculous. Can you use const where you used mutable here? No. Yeah, basically the default is const, so you say nothing. And then if you want to actually remove the const, you have to go up one more level in non-constness, so you go to mutable. It's slightly backwards, but yes, it would. Okay, so let's take it to the next level. This is everything you need to know about lambdas in C++ 11, and then some, because you have this whole init capture stuff. By the way, how would you do this in C++ 11 where we don't have this b equals 0 syntax? The answer is you make a local variable named b, you initialize it to 0, and then you capture it. All right, so let's kick it up a notch. Let's talk about generic lambdas. This is a C++ 14 feature. Let's see, what do we got here? I've got a template function. I should explain what generic lambdas are first. But this will be a decent explanation. Here I have a template function. It's called kitten. It has a local static variable called x. And again, it's returning x plus x, plus its argument. But it's now a template. So if I print kitten of 1, going to give me, let's see, 2, right? And then if I print kitten of 3.14, what does it give me? 4.14, right, excellent. Doesn't give me 5.14, why didn't it do that? And the answer is because we have 2 different x's. Why do we have 2 different x's? Well, we have 2 different kittens. We have the kitten that takes an int and the kitten that takes a double, right? They're 2 different instantiations of the same template. So they don't share anything, not even their static data. This rationale becomes more apparent because x doesn't really have to be an int, right? It could be anything. It could be a t. As soon as it's a t, now very obviously we need 2 different x's, right? We need one x that's an int and one x that's a double. So regardless, we have 2 different x's. Template instantiations do not share their code. They do not share their data. They're totally separate stampings out of the function. You need them to, you have to use a base class, yes, or a global variable, right? I could just make x a global, stick it outside the function. Question? Yes, I know that there is a proposal that will get rid of this whole template class T, et cetera, stuff and just allow you to write auto kitten, auto T. I believe it has not made it into 17. It may yet. I think it's pretty cool. I would like to stop writing template all the time. However, we're going to see. I think the next slide is going to introduce generic lambdas, which have this syntax. No, we're gonna first talk about. We're going to go through all the same slides, but we can go faster because you've seen them all before. Here we have class plus. It has a member function plus me, except now it's a member function template. Plus me is a template that allows us to stamp out a plus me of int, a plus me of double, any type we want. Excellent. We turn it into a templated operator paren. Now we can call plus of 42, plus of 3.14, whatever we want. Excellent. Now we take all that boilerplate. Oh yes, we make something nifty. We take all the reducible complexity. We get rid of it. We shrink it down to where we only have the irreducible complexity left. We capture value with value 1. We take something x of an unspecified type, and we return x plus value. This is a generic lambda. This is new in C++ 14. And it has exactly the same semantics as a class with whose name we don't have access to. It has a member function template for operator paren, operator paren const. Yeah, there you go. Generic lambdas. All right, let's go back to this puzzle. It would be cool if you could also get rid of the auto. Yes, although I feel like there is a strong prejudice against introducing names without some sort of keyword to say, like, this is a variable, right? If you like, there's nowhere else in C++ really except the capture list. In the capture list, we can just say value equals 1. We just made up this name value out of nowhere. Yeah. Yeah.
So the lambdas in D are exactly like that. You don't have to say the type. X, I return x plus whatever.
Yes.
Of course, nim as well. But nim is trying to look like Python for a systems programming language. So.
And for that matter, lambdas in Python, you can also, yes. You don't have to say the type. But that's a very different thing, right? Because Python is dynamically typed, right? It's got dynamic typing, it's got heap allocation, it's got garbage collection. Here we've got something that looks...
Typing is precisely accurate by Python. Duck typing, it's universal duck typing. It's not the same as dynamic typing.
I would disagree, but...
No, but I'm saying that it's not like Java, which is definitely dynamic typing. It is still effectively.
Well, then we're using different definitions for dynamic typing, because I would say that Java is statically typed but weakly typed, and that you have to cast anything to get anything done.
Well,
whereas Python is dynamically typed, and that you give me an object and I can do stuff with it. Like, I'll figure out what its type is on the fly.
But under the hood, Python is very statically typed.
JavaScript, where semantically objects are defined as collections of properties with string key. That's all they are. Like, Python is more going on.
Well, in JavaScript, you have things that aren't objects too, right? You have numbers, you have strings, right? Not everything is an object.
We're kind of off of...
Yes, we are. So here we have something that looks like Python in that we've got a function that takes a t, and we didn't even bother to say what the type of it was. We're just going to figure it out when we need to. But as you've seen building up to this, we never lost static typing. We never introduced memory management, right? We never introduced garbage collection. We've got this power within the language now without doing any of that stuff. Still have static typing. So here's puzzle number 3 again. We have kitten. It takes it's a generic lambda now. It takes t. It returns plus x plus t. So what does this print? 2 and 4.14. Yes. Whoops. I didn't actually update the numbers here, but yes, it says 2 and 4.14. So this is why I think going back to Jeroen's comment about that awesome proposal to get rid of all the boilerplate around templates. This will allow us to write auto kitten, auto t, and write this code, and think that we're getting something that we're actually not. Because in this case, we've written something without the template keyword, and it has this slightly surprising behavior. We've got a single entity, right? This generic lambda named kitten, and it has inside it something that looks an awful lot like a static local variable, but it doesn't really behave like one unless you're calling kitten with the exact same type. So it's a little counterintuitive.
So, question.
Yes.
What would be the analog of static
Static decal type of t, x.
Oh, that will be understood dynamically when.
Yeah.
evaluates it.
I mean, remember, this is not actually dynamically typed. This is actually statically typed. We know when we see the printf in main that once kitten of 1, we can say, aha. Oh, but you definitely can. That's pretty much the major point of decal type, is the fact that you can use it on something where you don't necessarily know the type, or you can't name the type. Yeah, if we, by the way, just because we don't know the name of a lambdas class doesn't mean we can't refer to it. I can have a lambda say kitten, and I can say decal type of kitten, and that will give me that is a type expression that sort of names that class. The fact that I can't actually know whether it's going to mangle to a $0 or $1 doesn't matter that much.
Another code. The other code doesn't know how to disambiguate the static.
Oh, yes, it does. What happens if you pass kitten to some other function? Let's say pass kitten to a function. Okay. Well, what's the argument type of that function? It's going to be decal type of kitten, right? I mean, it must be that. That probably means you got it from instantiating a function template, right? But your sort function doesn't say I take a lambda for my comparator. Your sort function says I am a template and I take a, type name predicate for my comparator, and you instantiate std sort with this particular, with decal type kitten, so that when you're instantiating it, it knows, he's calling the call operator with an int. That means it goes to this one. He's calling the call operator with a double. That means we instantiate the call operator for double, and so on. The magic of static typing, it does all work. And you might say, well, okay, but what if I want to pass kitten to something that's not a template? And we're going to get to that at what used to be the end of the talk and is now the middle of the talk. Can you pass an object to kitten? Yes, as long as that object, like a class, like an instance of a class, as long as it does something reasonable with the int plus that thing, right? It has an overloaded operator plus. You could also pass a char star, right? No, you could have a free function operator plus that takes an int takes 2 arguments, int and so the question, if I understand correctly, is what about inheritance? What about polymorphism? So if I have, I instantiate this for the base class, but then at runtime I call it with an instance of the derived class, what happens? And the answer is C++ already handles that for you. That's where you have virtual member functions and inheritance hierarchies and so on. You can do that, but you don't have to, right? And if you do that, and if plus in this case, let's pretend that we did reverse them so that operator plus could be a member function of the type. And then if that member function were virtual, if it were a virtual operator plus, then we would know that statically at compile time, and we would generate code to go follow the pointer and look up its vtable and call the right thing, and it would just do the right thing. And if it weren't virtual, then we wouldn't do that. Yeah, you can say auto ampersand t. You can even say auto double ampersand t. Yeah, I mean, well, if you're using polymorphism and inheritance and virtuals, and if you're doing Java, then you're probably passing around lots of pointers anyway, because like if I'm saying I have a reference to a base and I don't know whether this is, like if I have a shape and I don't know whether it's a rectangle or a circle, right? Then, I mean, I can't have it on the stack, because if I had it on the stack, I would know its size, right? So it must be out there on the heap being managed by some runtime thing. So at that point, I'm doing memory management already. And yeah, C++ is more and more hostile to polymorphism. Or it tolerates it, but the
Polymorphism should be restrained.
Polymorphism should be restrained, yes. Let's see. So you'll notice that none of these examples are actually using inheritance or virtuals or anything like that. I used them once pejoratively and called it Java, and I haven't used it since. And that's by design. All of this stuff looks a whole lot like it's dynamic, but it's not. It's all statically typed, and none of it is on the heap.
So going back to your previous explanation, then, if we pass in a triangle, that template will be instantiated for triangle, and operator plus will not be virtual. That will be triangle's operator plus, statically typed, statically bound.
If triangle is final, like they just added this final attribute, right? But I mean, maybe just because we pass in a triangle doesn't necessarily mean we're calling triangles operator plus. We might actually end up calling scaling triangle or equilateral triangles operator plus. We don't know, so it does still have to be virtual unless you do this attribute final nonsense. Polymorphism. Ugh. All right. So generic lambdas are just templates under the hood. I think we've fully established that at that point. Oh, and that's the end of part 1. And in fact, the end of the main part. That's everything you're going to learn about generic lambdas here. I'll now take further questions about generic lambdas. The obvious thing, the function with the auto argument, you mean a function template. So that template will be instantiated for that argument type, which is decal type of that lambda. Remember that the generic lambda still only has one type. Its type is $_0, right? Class $_0. It has a class type that is very well defined. That class's operator paren is a function template. Well, it will instantiate that accepting function for class $0. It doesn't need to instantiate $0's operator paren unless that function, the call E, actually uses operator paren. And as soon as we use it, we say, we now need to instantiate it. What are the argument types, right? The magic of static typing. That's true. That is true, but crazy, and no one should ever do it. Yes. Yes, I'm going to talk about std function and std bind eventually. But I like talking about std function because I feel like a lot of people are surprised by how it works, and it's just fun to talk about.
What we had C++ 11 was the best thing ever.
So std function. Oh. We're going to talk about bind after we talk about function. Function provides type erasure. So this is perhaps a more complicated slide than it needs to be. This is one of those ones that was added, and it has a lot of colors and a lot of lines. Yes, this needs to be better. So here I have I have our old friend plus, which I'm calling f plus for function. It takes an int and returns x plus 1. I also have the same thing written as a lambda. And the lambda L plus, what is its type? It's going to be some unnamed class type. What is the type of f plus? It's going to be a function taking int and returning int. Those are not the same type. And they can't be because one of them has captured this thing named value and the other one hasn't. So they have different types. That's unfortunate because they behave the same way. They're both things that take an int and return an int. And what I want to do, and in fact you can see that this slide is not well thought out, because when I say std function of void void, what I really mean is std function of int int, something that takes an int and returns an int. So pretend that this says int of int. The idea then is that I can take my f plus and wrap it up in something that will only specify, here's the interface. And I take my L plus and wrap it up in something that says, this is the interface. And they will end up with the same type. And this would be much clearer if this compiled. But hopefully it's still clear. What we're doing here is taking things of fundamentally different types, but same behavior. They both take an int and return an int, same behavior, but just due to the quirks of the type system, they have different types. And I'm going to wrap them up in something that erases that difference in the types and makes them appear to have the same type. This is like magic. How do I do this? But before, how do I do this? Why do I want to do this? I want to do this because of something we've already touched on, which is what happens if I take a lambda and pass it to another function. What happens if I cross a module boundary? I need some way of talking about lambdas, functor objects, callbacks, in some way that can cross module boundaries. Before I can implement sine and cosine, I need to say, well, what is their argument type? It's double. We're going to use double for all our math functions. Excellent. Problem solved. Then I implement some stuff that needs to talk about strings. How do I talk about strings? Well, I need to invent a type that whenever we pass a string across a module boundary, we're going to use it as std string. Or if we're Qt or Boost or any of these things, we're going to make up our own strings, and that problem hasn't really gone away. But if we had std string from the beginning, we wouldn't have had that problem. And so if we're going to make up things that pass around behaviors, callbacks, functions, things like std thread, right? The constructor for std thread takes, like, what does this thread do? That's a function that takes void and returns, presumably void, maybe int, I forget. So before we can talk about that sort of callback, we need an interface type that says, aha, I'm going to take or return a std function. Hopefully that makes sense. How do we implement it? Here it is on one page of code. So what are we going to do? Well, where to start? First of all, let's start in the middle. We need something that can hold an object of any type, right? Sometimes it's going to be a function pointer. Sometimes it's going to be a lambda. I need something that can hold either one of those. Okay, well, I'll just make a template struct container. Container of t can hold a t, right? Container of wrapped holds a wrapped. Done. Problem solved. Unfortunately, container of t and container of u are different types. And I can't, they're unrelated types. I can't use them successfully. Like I can't use them interchangeably because they're unrelated types. How do I make two types related? I'll give them a common base class. I make container base. I give it some virtual method. So here we are doing polymorphism. So I have a container base. It has virtual methods for the two behaviors I'm interested in, namely what happens when you call the thing and how do I destroy it, right? Virtual destructor, always a good idea. And our container of t, our container of wrapped, will override the call me behavior and say, well, what do? Well, we just call wrapped value. The semantics of this wrapped value followed by a pair of parentheses are determined by the magic of static typing, right? If it's a lambda, that means call its operator paren. If it's a function, that means like call the function. If it's a function pointer, it means dereference and call, and so on. Okay, so now that we have a container of t that we can use polymorphically, we just need to put one more layer of wrapping around that to hide that little implementation detail from the user. I'll call that class void void, which is equivalent to a std function of void void. And I can construct it with anything at all, right? This is a template constructor. Anything at all, as long as I can make a container of t out of it. And it has an overloaded operator paren. which is not virtual, right? Because it only needs the one, but it's going to call the virtual one via virtual dispatch. And it has a non-virtual destructor that calls the contained thing's virtual destructor. And there you go, type erasure in a nutshell. That's what it looks like in code. This is what it looks like at runtime. MyFunc is a std function object, or I guess a void object. It has one member, which is a pointer to this guy, who is a container of, in this case, an unnamed lambda type. And that guy holds the unnamed lambda and has a v pointer that points to a v table that records what do you do when you call me and what do you do when you destroy me. Those point to some code, and the call me code knows that through the magic of static typing, that it should call the call operator for the lambda. Hopefully that makes sense. Ironically, it's not possible to implement type erasure in Java.
You can do it with function.
Yeah, what Java calls type erasure is a totally different thing. Yeah. Right. This is very much like duck typing, except that again it's totally static. And the difference with like Python is that it can be dynamic at runtime. That instead of needing to stamp out instantiations of a template, which again we're still doing here, where there's still templates involved, templates and polymorphism, but still templates, right? Because we have to nail down all the behaviors statically at compile time. And what that means is that if I have two different things, I have two different lambdas, for example. I have a little lambda called kitten and a big lambda called cat. Then I can have kitten1 and kitten2. These are std functions that wrap things of decal type kitten. And I have cat1 that wraps something of decal type cat, which is a totally different type, and so it has totally different behaviors. Its container of the container of $1 is a totally different type from the container of $0. They have different vtables. They have different call me's and different destructors and so on. And we have pointers pointing all over the place. Notice that the two objects of type container $0, their v pointers both point to the same vtable because they have the same type. Hopefully that makes sense. And I think that is the last slide on std function. Questions?
You are aware that there are some implementations that use some union trickery to get around the small pipes and all that. Yeah, that's kind of the point. Is there are things that use unions to avoid some special cases of std function heap allocating.
Yes, you can do the small string optimization also here. We saw I was using std string earlier, and I just put hello in it. That's only 5 characters, 6 if you count the null terminator. That's only 6 bytes. We could just store that in. We have 8 bytes for this pointer to the heap. We could just take those 8 bytes and stick the 6 bytes right in there and be done with it. And then we don't need to do heap allocation for std string as long as it's short. And std function also has a pointer to the heap that takes 8 bytes. And if our lambda type, let's say, or I'm sorry, not lambda type, but our container type can fit in those 8 bytes in some nice unambiguous way, then yeah, we don't really need to allocate a whole thing on the heap. We can just store it inline on the stack in the space that we would normally be using for the pointer. Yes. Small string optimization works wonders in many, many cases. All right, let's talk about std bind. stdbind is obsolete and we shouldn't talk about it. How many people here have actually used stdbind?
A lot.
Fair number.
For the last, let's see, I started using tier 1 bind.
Well, as of last year, you can stop forever. So what does stdbind do? The idea is that I have a function that I've already got, like add. Add takes 2 arguments, but I want to make a function plus 5 that basically just, like, does the obvious thing, plus is 5 to the thing. So I'm going to bind add, and I'm going to say the first argument to this plus 5 thing, pass that to add, but for the second argument to add, just pass 5 directly. So this is the code in black there for plus 5 is doing the exact same thing as the code in gray. It is saying, I want a thing that will take at least one argument, call it x for the sake of argument, and I want to return exactly the thing that add would return if I forwarded x to it and then added 5 on the end of that. These are exactly identical. I went out of my way to make them exactly identical, even to the point of putting auto ... here and doing perfect forwarding and so on, just to prove that yes, you can do exactly the same thing with C++ 14 generic lambdas that you can do with bind. Now you might ask, why would I want to? I see this one takes a whole bunch of extra arguments maybe, and like I don't really need perfect forwarding if I'm just forwarding an int. And yeah, I mean, this is a template, like I don't really need that. I just need something that takes an int. Awesome. Then you don't even need bind. You could just use like regular lambdas. You don't even need generic lambdas. But if you need all the power of bind, it is there with generic lambdas. I'm not actually going to show you how bind is implemented because it is mostly boring, and you can pretty much figure it out given the fact that the syntax looks like this and does this. But I do want to talk a little bit more about bind and the pitfalls of it, just because Scott Myers talks about it and I found it interesting. So again, effective modern C++, this is item 34, right? He gives this example using a lambda. What we've got here is we've got this is straight out of his book, by the way. We've got a function setAlarm that takes a time, a sound, and duration, and says at time t, make sound s for duration d. This is an excellent candidate for bind, right? Because I might say, well, some of these I know that I'm always going to want them to be the same thing, so I like to bind them up front. So let me make a lambda called setSoundL. I don't know the sound yet, so I'll leave that unspecified. When you call setSoundL, you have to give me the sound. But I know that when you call setSoundL, I want the alarm to go off 1 hour from now for 30 seconds with the sound you gave me. And so you write this and it works. This doesn't use bind. This is something you really can only write in C++ 11 or later. So how would we have written this before C++ 11? And in fact, what I've got here, because it uses did literals and steady clock and all sorts of stuff, we probably need C++ 14 to write it. But pretending that we have all the library support, how would we have written this back in C++ 98 when we didn't have lambdas? Okay, probably looks something like this, right? SetSound B, function object, and we're gonna call setAlarm. We want the first argument to be steady clock now plus an hour from now. The second argument is the sound, so we haven't specified that. We'll leave that as a placeholder. And the third argument is 30 seconds. We want to go off for 30 seconds. Okay, great, done, right? We tried this code, it doesn't work. Not only it's already like looking a little bit worse. It's a little shorter, but the _1 instead of s, like it was kind of nice that we said sound s, and then now we have to say _1. That's right. We try this and it doesn't work because we've actually called stdbind with some arguments where one of these arguments is now plus an hour. That's evaluated at the time that we're making the call. So we try to call set sound B 45 minutes from now. The alarm is actually going to go off in 15 minutes, not the hour that we want it to go off. All right, well, fortunately, we can fix this. We can still use stdbind. We can make this work. How are we going to make this work? All right, defer the call to now. And the way we do that is we stdbind it. We say, I want something where when you call it, I'm going to get steady clock now. I'm going to get the thing that I would get if I called now with no arguments. Okay.
1 hour into it right there.
All done now, right? No. Now we have an operator plus here that's trying to add the result of bind, which is some random class thing, and an hour. And that doesn't work.
Yeah.
Yep. All right. Gotta keep going. Defer the call to operator plus. All right, there we go. This is how you actually write this code pre C++11 without using lambdas. It's got 3 nested calls to stdbind, and instead of saying plus, we have to say std plus.
Why do you need the expression on std plus instead of just using
Be more specific.
take the address of std plus with a specific type instead of doing brace open close brace expression form.
Take the address of std plus, he says. Std plus is a type. Std plus is a type template, class template.
Right, that's why you have to specify the type of class.
Well, and then what? And then : operator paren with an ampersand in front of it? I don't even think that would work.
You can bind it, but that's you have to have one more bind in there.
Yeah, so this is the corrected code. This works, but it looks horrible. And Scott Myers very rightly says, like, just don't do this. You just write the code the way that you want it to look, and you no longer need. What is the type of the first argument to set alarm? It's a time. Right. However, nested doesn't stdbind return a type. So when we call set alarm with the arguments that are this weird stdbind object and a sound and duration, like this weird stdbind argument is not a type. But stdbind has within it some more machinery that knows that when it's actually calling the thing, if any of the arguments to that thing are themselves bind objects, I should also evaluate them right now. This means if you have a function that actually literally does want to take a bind object, you can't then bind that function and have it do what you want, but that's acceptable, I'm sure. There's all sorts of weird hacks that have to go on in stdbind to do things that now are doable within the language. And I think that is actually literally, that is the last slide. So, well, in C++ pre-11, you didn't have a lambda. Yes, you could write a class with operator paren and so on that would do exactly this. And that's probably what you should do instead of using stdbind anyway. Which is why I have always been of the opinion that stdbind is silly and no one should ever use it. But as of 14, we can definitely say that nobody should ever use it.
A fully generic writing library in C++ would have been next to impossible.
But now you have seen that it's equivalent to a generic lambda, and you've also seen that generic lambda is a
C++11 now.
But you've seen now that bind is equivalent to a generic lambda, and generic lambda is equivalent to a class with a templated operator paren. So now if you want, you can take all your bind code and rewrite it as classes with templated operator paren, and it will just work.
You tried that. That's possible. Let me show you why, but there actually are some use cases with bind. Not generically possible pre C++11. loose interpretation of bind. So it requires re-implementing 3 different forms of the same function without bind.
Okay. So that is it. Lambdas and std function and std bind. Questions and otherwise dinner.